Yep. All right. Well, welcome everybody. Thank you for coming to the first lunchtime seminar of this summer for Luggage, Rising Stars in Energy and Environment. Primarily talk about what's outdoor stars in the community, and the way that they're selected for this kind of the black box. Essentially, I go out and ask the faculty, would you like to nominate someone who thinks of great research in their lab? And today we have people being nominated by Christopher Novellius, and Adelgren is one of our cool faculty, and Michael, who's an associated faculty, and we think we have different views. Aditya will speak first, and Aditya Aiyer earned his Bachelor of Science in Mechanical Engineering, with Master of Science in Physics from Aiyer Institute of Science and Technology in Goa, India. And then he had his PhD in Mechanical Engineering from Johns Hopkins University, working on the fate and transport of oil in the Deepwater Horizon Spill. And we were just speaking before that I got my undergraduate degree at Hopkins, and as a professor, I worked on problems related to the fate and transport of photo degradation over there. We had that in time, some sort of academic review for the academic. So for the past few years, Aditya has been a postdoctoral scholar with Michael Mueller on a project funded by the Aiyer Center to study the impact of wind wave coupling and how that affects power generation in offshore wind installations. And that is the subject of this talk today. Before I finish, I should say that after this fall, Aditya will be joining University as an assistant professor of mechanical engineering, with a lot of luck in this position. Oh, I should have said we have a few attendees. We have a few attendees virtually, and so for those folks, if you have any questions, please put them into the Q&A box. The chat function is also enabled, so if you would like to use that instead, I'll keep monitoring the chat and the Q&A box. When the talk is concluded, then we'll have to start answering questions from the audience and questions from people online.
So I'm going to stand here so that I can move slides from my laptop. But today I'm going to talk about some work I've been doing over the last 2 years. So really, where they kind of harness both the wind and the waves to explore some things about offshore wind energy. And this is work I've done with two collaborators, two co-supervisors, Michael Mueller and Aiyer. So the first question is, why offshore? So if you look at this map here on the right by Ender, you can see a resource map for wind speeds. And you can see both the east and west coast of the United States have very high wind speed, which is suitable for wind energy extraction. This is the wind speed at the hub height. And the second thing, as you can see on the left, there are no mountains, there's no land, there are no houses, there's nothing. It's a lot of available space to use and build these turbines. So you have faster wind speeds and more space, so you can generate more energy from resources. And there is a national target in the US where you want to have 2 gigawatts of energy by 2030. And we do have that much capacity. Currently, the estimated offshore pipeline is around 40 gigawatts. So we are going in the right direction to generate more clean energy offshore. So if you look at this graph here, you can see that historically the major leaders for offshore wind energy have been China and UK, and the US is somewhere down in the bottom. But this is improving. So there is a lot of under construction capacity in the US as of 2021, and this number is just going to keep growing. The hope is we also have like this exponential rise that matches the other graphs up there. And so there are key challenges involved which I first want to address regarding offshoring. So this is mainly in the fluid dynamics side, not the grid integration side. And that is, you have a very complex environment that you want to keep. So I won't talk about clouds and lightning in this talk, mainly the waves and the turbines, but I really like this picture that truly shows that there are a lot of things that can happen offshore that you kind of need to account for. And the main challenge is you have something like called separation of scale. So you have processes that are happening right from the meter scale, where you have the near surface wind-wave interaction that controls momentum transfer from the waves to the wind and vice versa. Then the next thing is you have the boundary layer itself and wind turbines, which are of the scale of say hundreds of meters. You need to resolve both the small part and the large part. If you go one step further, and then when you have these large offshore wind farms, you have these giant wakes of the order of a few kilometers that you also need to account for, because these wakes interact with each other and influence what the total power you can extract from these offshore winds. Right? So the question I want to address here and I'll talk about today is, why do the waves matter? And so very simply, what it does is it sets what the surface stress is of the ocean depending on the wave scale. And what that influences is the velocity profile in the boundary layer. And the power is proportional to the cube of the velocity. So depending on what velocity you get at the hub height, you will predict power. So this is something that is controlled by the system. The second thing is, you can also have direct influence of the waves on the turbulence and on the flow in the atmospheric boundary layer as it extends to around a wavelength of, I think, height. And if you go further offshore, you can expect waves to be around 30 to 60 meter wavelength. And so you can see that it's a considerable portion of the boundary layer that is affected by waves. You even have rogue waves or swell waves, which are these waves generated by storm systems that could be of the order of 100 meter wavelengths. And so that can also directly affect what's happening at hub. These control the power extracted. It informs what kind of control strategies you need to use in terms of pitch or torque control and stuff for your system. So it's important to study. And a very obvious effect that I've left for last is, when you have floating turbines, you need to know what the waves do, because that kind of defines your wave structure interactions, fatigue, load. So my approach here has been mostly computation. So just to tell you what computationally solving or modeling an offshore wind farm entails is, you need something to model the atmosphere, so the atmospheric boundary layer flow. You need something for the wind turbine. And then finally, you need something for the waves. So you have different subsystems that you need to couple and talk to each other so that you get this final offshore wind farm simulation. And typically what we do for the atmosphere is use something called Luggage simulation that I'll talk about soon. And for the wind turbine model, you can do different things to adjusting actuator line, actuator this. And the difference mainly is how accurate you want the near field characterization behind the wind turbines to be. That chooses what method. So for now, I want to focus more on low computational costs. So how can we do a lot of these simulations for realistic conditions to give us an input? So we mainly will use actuators. For the waves, again, you have different fidelity models that you can use. And again, the trade-off here is in cost. But the problem is that the low-cost models don't give good accuracy. So we need a better wave model to kind of address the effects of the waves on the boundary. So for here, what I'm going to talk about is something called wave boundary flows. And so what that means is, we want to characterize how different sea states or wave shapes influence the atmosphere in terms of momentum. And the way this is done typically is you specify the surface stress, and that surface stress depends on the wind velocity and maybe a drag coefficient. And in the atmospheric boundary layer, you can assume your velocity profile is high, roughly scales logarithmically, and you can use this information to extract what that stress is. And so you see, I've replaced the drag coefficient by the term in the brackets here. And now the key thing that you need to do is to define the Z0, which is the sea surface roughness. So it tells you how rough or smooth the ocean is at different surfaces. And that is what these two types of wave models do. So the phase resolve one numerically resolves each and every wave and calculates things extremely accurately, but with very high cost. So you can realistically do large scale simulations for the phase resolver. The phase average one throws off all the phase information and uses some sort of empirical formula to tell you what that Z0 is. But what we want to do here is to have something that will keep the phase information, but also give you information about the sea states and how that influences the boundary. So how do we do this? So we use a very simple approach that we say the effect of the wave can be treated as a hydrodynamic force being applied on the air side. And that force is proportional to the incoming momentum. So very simply, in simple terms, what this means is, if you have a flow moving from left to right and you have an obstacle, the obstacle is going to extract energy from the flow and impart a drag. And in this case, the wave is that obstacle. So you can do a simple control volume analysis, and you can calculate what is incoming momentum fluxes with the control volume moving with your wave. And you finally end up with an expression like this. So the details of this expression It's not that important that you understand every term, but roughly what it is you have a drag coefficient that is dependent on the wave sequence, that's the amplitude type, the wave number. You have some term which is proportional to the relative velocity. That means how fast is your airflow compared to how fast is your wave moving. Which seems obvious, right? If your wave is not moving at all, you'll have more drag. If your wave is moving as fast as the wind, the drag should be less because it's all kind of moving together. The relative velocity is zero. And then you have something that depends on the wave slope. So this is where you're incorporating all that wave phase information. And the way we do it is in our simulation, you just have it at the bottom. So you're using it as like a surface stress at the first grid point, where your waves are like these moving roughness elements imparting drag on the flow. Okay, so this is the main simulations we use here are called large eddy simulations. Just to give you a rough idea, when you solve for every scale in the flow, your energy is dissipated by viscosity. That's new here. So those are called direct numerical simulations. And when those are very expensive, so if you want to reduce computational costs, what you can do is say that you'll only solve for the largest scales of the flow, so the most energetic ones, and then you'll model all the unresolved effects. And what this does is it greatly reduces computational cost. But when you add a boundary in that flow, for example, the waves, it introduces another small layer right next to the boundary, which again becomes expensive to solve. So you go one step further and you want to model this effect also. And that's where wall modeled LES comes in. And what that does is it takes information from the resolved part of the flow. So those are the large scales, which are much easier to compute. And it uses that information to specify the effects of the unresolved portions at the boundary. So you're not really solving very close to the boundary, but you're using stuff from further away to inform what that stress would be at the boundary. Okay, so putting this all together, what you finally have is you're doing these large eddy simulations with a simple monochromatic wave at the bottom. And you're using, like, we use the wave model to specify the wave drag force, and then we want to see whether we can validate this with actual experiments and stuff. So the first thing I'm showing you is the wave stress. So this is a planar average total wave stress. So in an average effect, do we do a good job? The solid symbols here are from our simulations, and you can see a range of experiments with the open symbols, and you can see both qualitatively and quantitatively the stress has good agreement across different wave steepness conditions and also across different wave speeds. So you can see that the model does a good job in an average sense. The second thing is we want to see how much phase information we are actually retaining from this. So you can decompose your velocity as some time and spatial average velocity. That's that first term in angular brackets. Term just related to the wave. So that's that U tilde up there, and then a fluctuation. And if you just plot what your wave fluctuation velocity will be, you can see these alternating high and low momentum zones, which is correlated to the wave shape. So you actually feel the presence of the wave here in the model, and you get these kind of structures. And if you want to compare that with some experiments, you can see that you qualitatively have very good agreement. There are some discrepancies, and that's related more to that you have 2 points, for example, in the simulation, whereas for this experimental data, you'll have 15 to 30 points in that region. So you can get good accuracy with a much smaller compute. And so you can find that the flow is phase aware. And even if you look at mean velocity profile, so this is what's important when you actually go to look at the wind turbine power, you can see that it's also agrees well with the experiments. And so the takeaway from this is you have phase effects, you have a good agreement on average. And if you just look at, say, grid spacings and time steps, you can get up to 50 times savings in computation cost. So this is like the lower limit. You can also do much better. And this doesn't mean you completely replace the phase resolve simulations. This means that what you care about is not like 1 meter away from the wave surface, then you really don't need the phase resolve simulations to do the waves, and this model will work very well. So now what I showed you is for a simple sinusoid, right? But what do you do in a realistic ocean conditions? It's not one sine wave traveling along in a simple direction. What you really have is multiple waves of different wavelengths and frequencies, and they're moving in different directions also. And the way that is typically characterized is using a wave spectrum. So that just tells you how much energy is there in each frequency of the wave. And this is something that you can measure in the ocean and give you what the spectrum would be in a particular area. And so now the question is, how do you incorporate this spectrum into
Yeah, I'm just curious, is this an experimental spectrum?
So this is an empirical spectrum based on the Jones swap, like the joint North-West campaign. So it's one of those toy spectrums that people use. It's good for only very long fetches, so it's like there are other better spectrums that you can use, but it's just like to illustrate that this is one of them. It's an empirical one. So all these coefficients like alpha and gamma and all, they all fit to field observational data. Okay, so now if you want to say this model the full spectrum, for example, I've just shown like if you have two waves and you superpose them with a random phase, what you get is something like that. So it's not, it has some kind of complexities to it. Now imagine if there are like 50 waves or 40 waves of different frequencies superposed together, you'll get something way more complex. And so the way we do this is we first reconstruct the sea surface elevation by superposing a bunch of waves. And the resolution we choose is whatever we can resolve on a grid. So based on a computational grid size, you have a max resolution that you can resolve. And you can see on this, like this is just a representative sketch, but there'll be a lot of portions of the wave that you can't resolve. So a lot of small scale fluctuations that won't be represented on your grid. And we need to take care of that also, because the total force of your surface doesn't depend on what you're simulating, but what's there in reality. So it's a sum of both your resolved component and your unresolved component. And so now the question is, how do you put in this unresolved component back into your model when you have these realistic ocean cases? So we do something very similar to what's done for if you just have a monochromatic wave, is you have a roughness which is associated with the unresolved components and then use that as a stress. And the way that roughness is calculated is you can set it proportional to your RMS of your fluctuation. So you here, eta tilde is what's resolved on the grid, and you can calculate the RMS from the true eta versus what you filtered out, and you can get what those unresolved fluctuations are. And you know that your roughness has to be like, can be proportional to this. So now the game is how do you calculate this constant of proportionality without invoking any kind of empiricism? And we use a trick of self-consistency here. So what that self-consistency condition is regardless of what grid spacing I use in my simulation, the total stress at the surface just has to be the same. So if I resolve something at scale delta or I resolve it at scale 2 delta, the total average stress has to be the same because it's the same wave. And you get this, by using this equation, you get a self-consistency with one unknown, which is alpha, and you can solve for it during the course of your simulation. So this is like you dynamically update alpha as your simulation progresses. So you don't have to make any assumptions of its particular form. The only assumption here is that alpha is the same at both scales. So there is a scale invariance assumption baked in the self-consistency condition that your alpha doesn't change with respect to scale. Okay, so now we put this all together. I've showed you what to do with the atmosphere, what to do with the waves. Now, finally, you have wind turbines. We use like a very simple approach called the actuated disk model. And what it does, it says that the wind turbine is like a drag producing disk that extracts energy from the flow. And then you can calculate what that drag is based on simple momentum theory to be proportional to the area, the square of the disk average velocity, and some thrust coefficient. So this is the wind turbine model. And the thrust coefficient is something, it depends on your blade, the particular airfoil you use. And in simulations, we're kind of agnostic to it because this is information you get from experiments and tables of what the lift and drag coefficients are for particular airfoils. Okay, so now putting this all together, we have like a simulation for an offshore wind farm where you have an incoming boundary layer flow, you have waves at the bottom, and then you have a bunch of turbines at some configuration. And just to give you an idea of what the flow looks like, you can see all those blue regions there are where there is a turbine. So it's extracted energy from the flow, and so the velocity is smaller. So those are called the turbine wakes. And you see the alternate high and low momentum zones created due to the presence of these turbines. So just to give you some idea, I have like a simulation here for an offshore wind farm. They're just at different configurations. The important points here is like a wave of wavelength 60 meters. And you have your turbine hub height at 100 meters, and the diameter of your rotor is also 100 meters. So it's a 100-meter high turbine with encountering waves of 60-meter wavelength. So this is typical for offshore, deep offshore conditions. Okay, so this is like other like grid kind of details. And so the first thing you want to look at is just how does the flow look like? So you can see that it's a highly turbulent flow. You have like like a wake structure developing behind the turbine, that initially you have a low momentum zone, and then due to turbulent mixing, that kind of wake starts dissipating. And then if you look at the velocity variance, this is a measure of the turbulence in the flow. So it gives you what turbulence intensity is there in the flow. And you can see that it's very high near the edges as expected. You have more turbulence and more mixing near the corners. And also the magnitude of this increases as you go away from the ground. That's because you have your velocity also increasing. So you have a faster velocity hitting an obstacle versus a slower velocity hitting an obstacle at the bottom and top edges of the turbine. So now to look at something more concrete, you can first look at the wave stress. So on the left, I've shown you the wave stress without any wind turbines. So you can see that when you, for the same spectrum, you capture the peak wave energy, the peak wave stress in the spectrum. And as it your resolution limit is at K over KP2, and everything here is modeled. So you are capturing the peak. But when you go to the turbine case, because the turbines slow down the velocity so much, it actually changes how much of the wave energy you can capture. So what this means is, you can see firstly that the peak is no longer at the spectrum peak. That's because your velocity has reduced, and the peak of the drag doesn't correspond to the peak of the energy. And now if you didn't have that dynamic model, you would have never captured any of the effects which are less than which are higher than K over Kp equal to 2. And so you wouldn't have gotten any of those wave effects in the flow. And this can be seen in the mean velocity profiles here. So the black lines are from phase resolved simulations, and the green lines are from the LES with this dynamic model. And what I've shown also is, if you didn't have this dynamic model and had a very simplistic description of your setup, you wouldn't get the extra drag from those subfilter waves. And so you can see the discrepancy in the lower half between the simulations and the one without the dynamic model. In the upper half, everything's roughly equal, and that is expected, because you don't expect your waves to affect something 1,000 meters above the surface, which is the height of the domain. But you expect it to have some influence at the hub height, which is in the middle over there. Okay, so finally, I hope this can convince you that the dynamic model is necessary, and also you can simulate then the full wave spectrum in this form for realistic offshore conditions. And just to quickly summarize, so this is a wall modeled approach where you don't really have to resolve all of the waves, but you have a physics-based method to apply the correct stress. And you can do it for both simplistic, narrow-banded, and broad-banded spectrum. So it doesn't like derive the spectrum, but given a particular spectrum for the place you need to study, you can use this model. And this dynamic approach allows you to use it without having any kind of empirical tuning constants. And I guess the main takeaways then for the wind part is, now you have some model which is now 10 times cheaper than what people do for wind turbines. So wind turbine simulations are anyway very expensive. And now when you add the wave solver, it becomes even more. So it's 10 times cheaper just based on grid spacings you can use when you use this model. Something that I'm not showing here, which also adds to the cost, is all these phase resolved models have a separate wave solver. So they have something for the airflow, but they have another potential flow solver for the waves that also adds into the cost. It's also very simple to implement because you don't have any grid following or remeshing stuff that you need to do. And so these are things that can easily be taken and has portability across different kinds of simulation codes and can be tested very robustly in that sense. So with that, I'll be happy to take any questions. Thank you.
We're gonna have 5 minutes for questions.
So maybe a very naive question. So in the model, I think you assume the wind and the wave are unidirectional, right?
Right. So in the results I showed you here, that was the case, but it can actually be misaligned also, because you apply the drag force in the horizontal plane. So if the wind waves are misaligned, you can account for that in the model also. So it doesn't have to be unidirectional.
Thanks.
That's a very simple, probably a very simple question. How should I physically interpret wave stress and surface stress?
Right. So the wave surface stress, the way I think about it is, I think of it as like there is some obstacle that extracts energy from the flow. And so in that terms, like if you have very rough waves, you're extracting more energy, and so your airflow is slower. And if you have waves that are moving much faster, you're extracting less energy, and so you have more airflow. It's kind of how I think. It's very hard to then imagine stress in that sense. It's more easy to imagine a force. And you can relate the two, you can just integrate the stress over the volume and you get the force kind of thing. So that's kind of how I think about it.
Maybe also you mentioned it at the end, but I wanted to ask. So in a given simulation, the forcing, you're given forcing from the simulation that comes, are there two forcings, one from the wind, one from the waves, or are the waves like coupled and there's only the wind?
So there are two forces. So that's a good question. So the way the wind is generated is you have a constant pressure gradient across your channel that develops like a boundary layer flow. So you have a boundary layer flow that's developed by that pressure gradient, and the wave effect is through the wave model. The waves are not coupled to the flow in the sense that the wave is prescribed. The shape of the waves don't change, and there's no like two-way information from one to the other.
Another question? I have one more question, which is for the wave spectra. They have you explored others besides the one empirical one that you showed us?
Yes, we have. I mean, the problem there is it's hard to find data to compare because the data when you from field observations, you can't get very close to the ground. And so when you look at the velocity profiles from then, it's mainly like straight lines because you don't have that bottom part, which is kind of giving you most of the action. And then when you go to compare with those field observations, basically you can tune a constant that shifts your line back and forth. So it's not that robust in that comparison. So right now we've been limited to only comparing with phase resolved simulations for the full offshore case. And that's what we just like use the spectra that they already use. But I think this is something that is an effort that people are making right now, is to get like these better measurements closer to the surface. And then that would be a candidate to like explore how this model does for realistic field observations.
Are they collecting those using remote imaging?
So there are two. I think now what they're trying to do LiDARs also to do it, and there's one which uses the satellite interferometry to get like what's happening at the surface. But the way they reconstruct the surface stress, there are two different ways. You can construct it based on like measurements 10 meters above, or you can calculate like you can put pressure probes and reconstruct it. And those also give you slightly different answers, the way you reconstruct the surface stress from these measurements. So I think that's like it's actively being researched on how to get robust measurements from different kind of measurement techniques to give you the same answer.
So your wind can't couple back to the waveform.
Yeah.
Just said, but in principle, the turbulent wave behind these does, create wind fluctuations that can alter your waveform.
Yes, yeah. So they could, and that's a good question because these wakes are very large, and for very large wind farms, you can have them extend towards the surface, and then they would definitely alter the stress that you have there.
But you have information from the simulation now that can estimate.
Yeah, you can estimate that stress. Correct.
What the fluctuations near the surface are due to the wind.
Yes.
And if you expect that to alter.
So the problem here is like when you go offshore, right? The time scale which requires for waves to change is much larger, and so most of the time they don't get influenced that much by the wind turbines. But there are like in terms of changing the stress, it does influence it, and so there could be some coupling that drives now even subsurface flow because the surface stress distribution is changed because of these wind wave interactions.
What's that time scale?
Like for example, like the waves present in a particular offshore location, they have been generated. A wave fetch is where the waves were generated. So they've probably been generated 10 to 50 kilometers away and travel to that location at some particular speed. So for the wind turbines to alter it would be of the scale of maybe it'll be days and stuff, but by then it's already a new thing.
Fernando, so one more question. Then how about when you're asking that? Maybe we'll switch you up and get to this one.
You have two scalings for the computational cost. One that is the Reynolds 9/4 and the other 0.4. What's the difference between that?
Right. So when you do when you don't do DNS, like you don't have viscosity. So technically, large Reynolds number LES is Reynolds number independent because you don't have any viscous layer you need to resolve. When you put a wall, you again get a Reynolds number dependence because you have a viscous layer near the wall. And so wall resolved LES is almost as expensive as DNS.
I see.
And now in wall model LES, you're again removing that viscous layer and modeling it. And so you again are roughly Reynolds number independent, but it's like a 0.4. It's a very weak scaling of
So the difference is just just having the wall.
having the wall. Yeah.
Thank you.
Thank you, Kevin. I realized as I was sitting there, I have to introduce myself. I'm Charlie Sharpless. I'm the Assistant Director for Research here at the Aiyer Center, and I'm the organizer of this seminar. Next up, we have Nate Adelgren. Nate earned his Bachelor's in Science and Mathematics from SUNY Fredonia, which is State University of New York, if you're not familiar with it. He then earned his Master's of Science in Applied Mathematics at it's Indiana University of Pennsylvania. Yes, I abbreviated it. Abbreviations. And he went on to earn his PhD in mathematical sciences from Clemson University. After that, he took up a faculty position as assistant professor and then was promoted to associate professor of mathematics at Edinburgh University of Pennsylvania, which is primarily a teaching position. And after a few years there, Nate decided he really wanted to return to more research-based work and came here to Princeton as a postdoc. He was an associate research scholar working with Christos Maravellius in chemical and biological engineering in 2021. Christos' group mainly works on, I would say, problems in mathematical optimization related to process and industrial efficiency that have to do with energy and chemical and fuels. And Nate is going to speak today on a problem related to essentially shipping and 3D packing that is a kind of process and efficiency problem. Again, I expect this at the end. That's the way my notes went, but Nate will be leaving us after this year to begin as an assistant professorship in the mathematics department at the Naval Academy in Annapolis, starting this fall. So good luck in that position.
All right, thank you. Yeah, so I'll do a similar thing. I guess I'll stand on this side since where I was sitting. So yeah, I'm going to talk about two different container loading applications. One is kind of a more general offline approach, and then later in the talk, I'll come back to a more online real-time approach that has a specific application for airline loading. So in the first part of the talk, I'll just give a quick overview of the problem and why we want to solve it. And then I'll give a really high-level problem statement and talk about the optimization model that we use. I'll spend a couple of minutes highlighting some of the constraints that need to be modeled and how we think about them in a little bit of a novel way in order to get what we want to happen. And then I'll talk about a heuristic approach that we sort of merged with our optimization model in order to make our results be able to be achieved a little bit more quickly. And then I'll shift gears and I'll talk about the airline application and the real-time loading of luggage, why that application needs to be feedback controlled, some of the methodology that we use in order to replicate that, what happened when we incorporated a heuristic, and then I'll end the talk talking a little bit about compressibility of objects and why considering that it's really important to be able to achieve some of the targets that we have. And then we'll conclude. So just the problem that we're looking at solving, I mean, it's just we have a set of rectangular objects, we know their dimensions, and then we have a set of rectangular containers, and we want to move all those objects into the containers. Then, of course, we have these real world constraints, right? So we have like weight distribution constraints, we have stability restrictions, we might have some restrictions on orientation and things like that. So if you don't have a picture in your head yet, you can look down here at this right image where you have like these rectangular objects that need to be loaded into this container. So we come up with some kind of like packing scheme that should okay, but anyway, these objects are all supposed to move into this container and
Use the mouse.
it's actually just supposed to be a GIF that plays automatically. But anyway, just pretend that you can visually see in your head of all these objects moving nicely into this container and all fitting at the same time. All right, but anyway, so when Siemens, the company that we're working in collaboration with to solve this problem, brought this problem to us, it was August of 21. And you can see from this graphic over here, the freight prices were through the roof. So it made a lot of sense to Siemens. If we can ship fewer containers, we can save a lot of money. On top of that, we know that 8 to 11% of global greenhouse gas emissions are due to freight transportation. And then as we get to the end of the talk, the automation procedures are, of course, designed to increase efficiency, reduce costs, and improve the safety of our working environments. So again, this is an optimization model that we're using here. In reality, there's probably tens or even hundreds of variables that are wrapped up in the model, but just some of the really key ones that I'll give you. Of course, we have X, Y, and Z. This gets the location of the lower left-hand front corner of each object. And then we have an O variable that represents the orientation in which an object is placed, right? So it can be placed like this, or rotated on its side, or flipped over and set on its bottom, something like that. So of course, with any typical optimization model, we have some objective function that we want to maximize or minimize. I've listed a couple of potential candidates here. The one I'm going to focus on today is the second one. So maximizing the total volume of the items in a container, and then sort of iteratively solving. So if not everything fits in a single container, we store those extra ones in some back closet or whatever, and then load them into another container later. So we have all of these restrictions that show up in real life that we also have to consider. Some of them are very, very simple or obvious, like when you have objects, they can't occupy the same space, they can't overlap, they all have to fit inside the container. And then we have others that are a little bit more complicated or are application specific, right? So we have some objects that can't be rotated in certain orientations. So you can think of, you see a box that has an up arrow, right? And it says this direction up. So it has to be stacked in that way. Or we might have position restrictions. So if you have some kind of like truck shipping application, you might have objects that you want to store near the doors because they're going to come off first or something like that. Stability restrictions, so we don't have things that are falling over that shouldn't fall over. Fragile items can't be stacked on top of, weight distribution considerations, and overall weight limits. So the novelty of this work really isn't the constraints that we're considering, although there is something to that I'll talk about in a moment, but really the fact that we're considering all of this stuff at the same time, right? Because in the literature, all these things have been proposed, but most applications don't consider them simultaneously. So there's a big challenge in trying to do that. So I'm going to highlight one of these in particular, and it's going to be the stability restriction, because for a couple of them, in addition to the fact that we're considering them all together, we also think of them in a little bit of a different way than they're thought of in most of the publications in literature. So up on the top right here, you see an image of a packing application where stability restrictions aren't considered at all. Right, so you have objects that are like floating in the air, or they're almost definitely going to fall over as soon as we let go of them. And so, of course, there's a need for a stability consideration. So the two things that are done in the literature are a vertex-based approach, where we pick some number of vertices that need to be supported. When I say supported, I mean they're either on the ground or there's an object directly below them that doesn't fall. Right, and so usually that number is 3 or 4. Or there's a percentage-based approach where you specify that a particular percentage of the bottom surface of an object needs to be supported from below. So I'm going to do a couple of quick thought experiments to show you why these two approaches are a little bit lacking. So in this first one, you can see like a side view of a packing scenario and a top-down view of the same thing. And of course, in a vertex-based approach, this is a valid packing, right? But as soon as you try to switch to a percentage-based approach, there's no way that you would ever want this to be valid in a percentage-based approach, because there's probably less than 25% of the bottom surface that's being supported. And so if you take that approach, 25%, and you allow for other things to satisfy that same restriction, you're going to get a bunch of stuff that falls over, right? But now take like an alternate view and a different packing scenario. So in this one, we've got a great percentage of the bottom surface that's being supported, but we don't have the 4 vertices, right? So you can see from these two scenarios that like neither one of these two approaches is very holistic on its own. So what we did was we said, let's consider a vertex-based approach, but let's change what we mean by supported. So I'm going to call it pseudo-supported, and we're going to allow it to be somewhat user-defined. So imagine in this image that I've displayed here that we're looking at a top-down packing scenario. This kind of like pink object that has its outline over here is something that we want to stack on top of something else. And I'm going to call a vertex pseudo-supported if the object that's supporting it from below intersects this dark blue region in any area, right? So then what we can do, and this probably won't play because the other one didn't, but by modifying the support parameter, we can allow this dark blue region to extend as far as we want it to up till the entirety of the box is consumed by dark blue. And so in both of those packing applications that we saw a moment ago, right, by allowing the vertex to be pseudo-supported, the first one would be obviously supported, and then the second one where we just have a little bit of overhang on the edge would also have all 4 vertices be pseudo-supported, and therefore both of those packing scenarios would be valid using this type of constraints. So we did some other things for the weight distribution constraints and some of the other sets of constraints where we sort of modified the way that we thought about them. But again, the power here is that we're putting all of these things together all at the same time. So with that, we had a pretty good optimization model that we're happy with. And of course, the difficulty is with all of these constraints considered simultaneously, it takes forever to solve, right? So we implemented a heuristic, but not exclusively a heuristic, like it's frequently done in industry. So we merged the heuristic approach with our optimization approach so that we could, get the benefits from both. The heuristic approach is pretty simple. I'll just explain quickly. So we randomly order the items, place the first item at the origin, which is this dot in the upper image here. And then each time a new item is placed, we generate a set of candidate points where new items could potentially be placed. And I don't know if you can see it in the image, but all these little dots that show up are candidate points where additional items might be placed. And then we maintain those candidate points in some sort of sorted order. It doesn't really matter how you sort them, they just need to be sorted. And then we place subsequent items at the first candidate point where they fit, and in the first orientation in which they fit. And so using an approach like that, we're able to generate valid solutions in fractions of a second. The difficulty or the problem here is that the solutions, although they're valid and they're quick, they're not anywhere near optimal necessarily, right? So these are 25 items that should fit inside this container, but the heuristic approach, this kind of plate right here is supposed to be the back wall of the container. 2 of the items don't fit, right? So we can merge the heuristic with our optimization by converting it to a genetic algorithm. So we change the order in which items are placed. We can call the genetic algorithm periodically throughout the optimization process using the optimizer's callbacks. And then we can provide those new solutions to the optimizer in order to help move it along. So a couple of results here, I suppose. So this is the same scenario where I have 25 items I want to pack. Again, this solution is generated in a fraction of a second. Back here, what you're seeing is a couple of objects. They're not supposed to be floating in the air. They're supposed to be set on the ground in the back. So they're sort of saved to be packed in another container later. If I run the same scenario using only the optimization without the heuristic and let it run for 5 minutes, I get a very different orientation for all of the items, but essentially the same result. There's a couple of objects that weren't able to be fit and need to be saved and stored in another container later. But when I put the heuristic and the optimization together, this solution is generated in just about 30 seconds, where all 25 objects are oriented in such a way that they can be placed within a single container. All right, so here's where I'll switch gears and I'll start talking about automation of this process, and particularly an application for airline load. So after we've been working on this previous project for about a year, Siemens came to us and they said, hey, we have some colleagues over in Germany. They're working in our airport logistics division. And we think that the application that they're working on would be a great, thing for your application. So your algorithm that you're working on is really good foundation. So the idea is that when people check luggage at the airline or at the airport, they're loaded into these universal load devices or ULDs. And currently that process is done by humans, right? So the objects show up on a conveyor belt and people manually load these ULDs. So Siemens said, we'd like to automate this process. We'd like to have robots, we'd like to have perception systems, video cameras, things so that we can get better tracking, so we can get better efficiency, we can save people from getting hurt and all these kinds of things. And we said, okay, great, but why aren't you doing that already? And they said, these two issues, right? So deformability and slipping and toppling. Basically, the applications that people have been working on were very similar to what we had been doing, where you know all the items ahead of time, you come up with some packing structure, you start putting stuff in. But we all know luggage has like a smooth surface like this kind of, right? So you start packing things on top of each other and all those smooth surfaces start like slipping and sliding, or objects that are sort of compressible are loaded with clothes and you put something heavy on top of it and it sinks. So when the state of your system changes, according to the packing plan that you had previously decided you were going to utilize, the robot doesn't know how to handle that, right? So now it's trying to place something on top of something that's no longer there or whatever. So a human at that point has to be, used to come in, fix the packing state so that it's what the system thinks it should be, and then continue packing on top of that, and that's not very efficient. So we said, okay, we know how to fix those kinds of things. We need some feedback in the system, right? So I'll talk a little bit more about what this is going to look like, but now you can picture you have some kind of like 3D version of a Tetris game, right? Where you have something that shows up on the screen, and based on what's below it, you want to give it a position, right? Based on where you put it, things might change, right? You might eliminate some lines or whatever, but that doesn't really matter to you because when the next item shows up, you just got to stick it somewhere according to what has happened. Okay? So a couple of targets I'll mention. They wanted us to be able to match human speed, so 18 seconds per item, and they wanted us to get 90% or greater volume utilization. And I put an asterisk here because this metric has not been well defined throughout the project, and that gives a lot of headaches, and I'll talk a little bit more about that as I continue. So how does the feedback control system work? Well, basically we have a perception module that does two things. It scans luggage that's arriving on the conveyor, and it tells us what the dimensions of the luggage is. And then the other thing that it does is it scans the ULD, and it tells us about the current state of the system. So it tells us where things currently reside. And then that information is then passed to packing module, which is our contribution. So we're using the Garobi optimization software in order to determine a particular packing plan. And then that packing plan is shipped off to a robotics module that's tasked with actually implementing the plan. I'll give a little bit more nuance to the approach in a second, but that's the basic idea. So in terms of implementation, that's kind of represented using this flow chart. So we start with an empty ULD. We then get data about n items that are on the conveyor. So throughout the rest of the talk, unless I say differently, let's suppose that n is 5. So we know the dimensions for 5 items. And then we're going to compute an optimal placement for those 5 items with the restriction that the first item that comes off the conveyor needs to be in a position where it can be packed, right? So when I pack those 5 items, the first item can't be on the top because then it doesn't make sense for the robot to try to place it there because it's just going to fall. So then we check to see if any of the items fit. If they do, we simulate the robotics module, which is basically just place the item where it's supposed to go. And then we simulate the perception module just by writing back and forth to some spreadsheets. So of course, this would, obviously, these things would be taking the place of in a realistic application, and there may be some other simulation that could be utilized in between here, like a physics simulator that says, okay, this object's going to fall and the current state of the system should change and things like that. But once we pass the information back from the perception module, what we have is just a height map. It's just like for every XY point, we know the height at that current location. Right, so we convert that to some set of mock items or that are used within our optimization approach, and then the process repeats. So I'll just talk about a couple of nuances here for a moment. And one is in terms of knowing about 5 items. So we do assume that when we're developing this packing plan that we're going to pack all 5 items. Right, you can think about the Tetris game, right? So when you have a particular item that shows up, you figure out where to put it. But in some versions of Tetris, you not only know about that item, but somewhere on the side, it tells you about a couple of other items that are coming, right? And so if you're really good at Tetris, knowing what stuff is coming might change where you want to put that first object, right? So, so we do assume that we're going to pack all 5 items, give them all locations, and then after the first item is packed, we redo that. So even though, so we really only physically place one thing, but we're always considering 5 objects at a time when we're coming up with our packing plan. And the other thing is that during this phase here, where I've called it an optimal placement, I've put an asterisk because this is where we have to really simulate real life, right? So we can't spend 5 minutes trying to figure out where to place 5 items because we need to match this 18 seconds per item, right? So here we put a 10-second time limit on the optimization and just take whatever solution it gives us at that. All right, so here's some results that we've obtained throughout the course of the project. So it's kind of going chronologically left to right. So what we did is we developed 50 data sets, all containing 50 items to be placed within a container. And we run the optimization algorithm using 4 different objective function alternatives. So those are the 4 different lines in the images. And we measured the volume utilization. So the volume utilization in this sense is like the true volume utilization, where we sum up the total volume of all the objects and divide by the volume of the container. And on the y-axis here, we can see the percentage of the instances where we achieve a particular volume utilization or higher. So for the best performing objective function, like 70% of our instances, or sorry, about 45% of our instances are solved to a 70% volume utilization or higher. So early in the process, we weren't getting very good results. We weren't anywhere near that 90% volume utilization target. We were also taking way too long to pack each item. So we cleaned up the code. We added some different considerations into what constraints we were using and how we were implementing them, and made a variety of changes in order to obtain much better results, right? So we're now packing 7 seconds per item, and we've increased at least the best performing objective to get a little bit more volume utilization. So now we've achieved, what we want in terms of timing, because if we can give a packing location in 7 seconds, then certainly a robot can move that object within 10 seconds if you packed in under that 18 seconds. But the next goal is to try to reach that 90% volume utilization. And so I had a couple of ideas as to how we might try to accomplish that. But the first one was this idea that I've been talking about with Tetris, right? Where if we know about more items ahead of time, then maybe we can come up with a more strategic idea of where to place them. And so that is what you're seeing in this graphic here. So the 2 is if we know about 2 items ahead of time, 4 is know about 4 items ahead of time, and so on. And you can see that kind of what I hoped would happen happened at first. When I know about 2 items, I get decent performance, but when I know about 4, I get better performance, and when I know about 6, I get better performance. But then it degrades from there. And what happens is the optimization problem just gets so hard that we are exiting after 10 seconds before getting anywhere near an optimal solution, and yeah, just terrible performance. So in order to try to combat that, I'm not going to go through all the details, but we incorporated a heuristic in a similar fashion to what we did in the first project I talked about. And it didn't do exactly what I wanted to do. I was hoping that, you know, with a 12 or 14 item look ahead, I'd really get that 90% volume utilization and everyone would be happy, but that's not what happened. And it kind of makes sense if you think about the Tetris game too, right? If your screen lines up with like 10 items that you know ahead of time, I mean, it's just overwhelming, right? There's too much information. It's not really going to be that helpful. So we got over that hump of performance degradation because we weren't getting anywhere near optimal solutions. But now we're sort of plateauing where we're not getting better performance because we know about more items. So the last thing that really, I guess I had in my back pocket at that point was, well, what about compressibility of the items? So we got a hold of our colleagues over in Germany and we said, can you do an actual experiment for us? Can you load real luggage with real clothes? Can you put it in a real ULD? And can you tell me what happens? And they said, sure, we can do that. So they took 45 luggage items, load them with clothes, stacked them in the ULD. So they didn't use any kind of look ahead limitation. So they knew about all the items. They just picked which one they thought would be best for each location and so on. And so they came back to us with the data a couple weeks later, and I asked 3 questions. I said, first of all, you know, does anything compress when we put heavier items on top of it? Do we get any compression? Because that would help me. And I was really surprised by this number. They said on the bottom layer, we got up to 25% compression for the items. I was expecting 5 or 10%, but they said 25%. So I was really impressed. The other 2 things I said were, 1, do you consider this ULD to be full? And they said, yes, we do. We fit 45 items. There's not a lot of room at the top. I said, okay, what's the volume utilization? And they said, we don't know. So I rolled my eyes and face palm for a little while. And then I calculated the volume utilization and I told them, your volume utilization here is only 78.72%. So if this is what you're achieving and you're calling it full, why are you telling me I need to get 90% volume utilization? And they said, we don't know. So basically what I think is happening is they have some competitors on the market that are saying we can achieve some 90% volume utilization, but they don't have a real metric that they're using. So they came back to us and said, look, just call it full if we get 42 items more. Fine. Okay. So I did a couple of things to try to analyze compressibility to see if I could kind of get better results. And so the lines that you're seeing here are all based on assuming that every object being placed in the container can be compressed to a certain amount in the Z direction. So its height is being compressed. And so you can see, I mean, it's pretty intuitive, I guess, as you increase the amount of compression for each item, you're increasing significantly the volume utilization because you're using the original dimensions of that object when you're computing its volume, right? You're not using its compressed dimension. But this, of course, isn't realistic. So then I went ahead and looked at what happens if I want to consider things on the bottom being compressed more than things at the top. So I just implemented like a linear change in that compression factor. And to be a little bit conservative, I said at the bottom of the container, we're going to assume 20% compressibility. And once we get to 130 centimeters, because the whole ULD is about 160 centimeters, we're going to stop. We're going to say compressibility is 0. And these are the results that I've seen. So I'm not hitting their original 90% volume utilization target, but I'm well over their 77% that they got and told me was full. And I'm doing quite good, I think, in terms of timing, because again, this leaves about 8 seconds for a robot to be able to manipulate the item location. And that's where the project stands at the moment. So with that, I'll conclude. So I talked about a couple of new constraint formulations that help increase applicability of the container loading problem. Talked in both applications about how merging a heuristic with optimization can improve performance. We have successfully simulated this feedback control system where we have a perception system and a robotic system. And our current results, I think, look pretty good, but I guess that's for students to decide. All right. Happy to take it.
Why wouldn't you scan the dimensions of your items when you drop your bags and have some kind of sorting system, which would allow you to, I guess, use 1 hour or something to optimize?
Yeah, that's a question for airport logistics, right? So they don't have a system like that at the moment. But you're absolutely right. If they could give you an hour, that would be great. But I think oftentimes, you know, you have that last guy running down the runway that just checked his bag 2 seconds ago in the
80% or so of the bag it wouldn't work, right?
Yeah, so if you had people that were all on time, maybe it would work.
So the first problem you're talking about, the offline one, is that just non-convex side? That's so hard.
The way that we've modeled it's linear, but I mean, almost every variable is binary.
Okay,
So it's huge. It's like hundreds of thousands of variables.
okay, so it's mixed integer and it's just really hard to solve this.
Yeah, so what happens is, the formulation, when you have all these constraints put together, depending on what optimizer you're using, so Kurobi is pretty good at finding heuristic solutions, but it's terrible at closing the upper bound or the dual bound, right? It never closes that gap. So it almost never proves optimality, even though you would think that being linear shouldn't be that hard.
Yeah, it's just really simple. You know what the average actual compressor, I mean, did they do that test with all software luggage?
No, actually we have pictures, it's a variety, some are hard, some are soft, but the thing is, like, not all the objects are going to compress to the same amount. More so what really happens is you have a layer of luggage that's all kind of varying in its height, and that just sort of levels out over time. Yeah, no, I don't have an average.
No, we're not on. In a very fancy version of, you have an in-between system. That's
For sure.
object, so that was typically.
Yeah, and then there's other things that you can do, like we've looked at reinforcement learning approaches to try to, you know, take away the difficulty of the optimization and try to say in real time, where should this be placed? Just get a input and output from a neural net, but we haven't gotten good results at this point.
None of the online questions, so. Thank you again. And we'll have our next seminar in, let's see, 2 weeks. Basically, right at what I'm trying for, we're gonna do another week after that, and it's July, and we have a good job. We'll have the next seminar, and then we'll send out an announcement about that. Hope to see you guys there.